Welcome back. So in this video, I want to transition from talking about sound to talking about light and comparing our sense of hearing to our sense of vision. So the reason why it's interesting to compare these things is that sound and light are actually very similar physical phenomena. They're both wave phenomena. And so I'm going to talk in this video about just the basic physics of light. What is light? And then in the next video, we're going to talk about how we characterize light like we did for sound. What are the properties of light and how do they relate to basic wave properties? And then we'll talk about our sense of vision and how that compares to our sense of hearing and why those are two very different senses for us. And so in order to tell the story about light and what it is, I have to go back and remind you or tell you about some basic electromagnetism. So in the next few slides, I'm going to remind you of just some of the basic ideas through which our universe operates. And so we've talked in the past about various forces that cause things to move or stop moving. Most of the forces that we encounter in our everyday life actually have to do fundamentally to the forces of electromagnetism, to forces between charges. Okay, so the basic idea is that there's this fundamental property that matter can have that's called charge. So the protons and electrons that are making up the atoms that you're made of, they have this property. The protons have a positive version of this charge. The electrons have a negative version of this charge. And charge is something that's conserved. You can't get rid of it. And so like energy and momentum and spin, it's just there. And if you have a bunch of particles, then the total charge is the sum of the charges. And so the thing that you probably know is that like charges repel and unlike charges attract. Okay, so when you take your sweater out of the dryer and there's a sock stuck to it, it's because the sweater overall has some positive charge and the sock has some negative charge, or the other way around. And so there's this force, there's this attractive force between those two. And similarly, when you have two things that have the opposite charge, then they will repel each other. So what's important for us in this discussion is how does that work? Where do these forces come from? And so there was a deeper understanding that physicists worked out, well, centuries ago already, that the charges are producing these forces on each other because of something called an electric field that they create. So here is the basic picture of that. I've shown a positive charge, and so the idea is that that is producing this invisible entity that surrounds it that we call an electric field. And a way we can represent this is as a bunch of arrows that are pointing in certain directions and have certain lengths. So what the arrows represent are the forces that this electric field would exert on some other charge, on some other positive charge. So the arrow shows the direction that the force would be in, and the length of the arrow shows how strong of a force you're going to get. And so in the picture, you see that the electric field produced by this positive charge is everywhere pointing away from that, and it's smaller the further away you get from the charge. And so this other charge that's positive feels a repulsive force. It's pushed away from the first charge. And the other charge that's negative feels an attractive force. It's attracted towards that first charge. So the electric field is the first important idea we need in our discussion for understanding light. Well, there's a similar thing that has to do with magnets. So we've also talked about the forces between magnets that depending on the orientation of the magnets, they could attract or repel. And so our understanding of this magnetic force also involves a force field that we call the magnetic field. So this is something different than the electric field, but it can be represented in the same way. It's an invisible thing, but we can represent it by a bunch of arrows, and the arrows basically show us how strong this field is. So how strong are the forces that the first magnet is going to exert on some other magnet that we bring close by. And it shows us the direction of the force. So if you have another magnet with the same orientation, then it'll be actually attracted. And if you look at the arrow, that will show the direction that it will be pulled, or the opposite direction of the arrow is the direction it's going to be pulled. Now, one thing we've talked about, just as an aside, in the past we've talked about how not only magnets but also electrical currents can produce these magnetic fields, and it's the same physical entity, the same kind of magnetic field. So when you have the electrical current, it also produces something that can be represented by these arrows, and those would have the same effect. They would exert forces on any other magnet that you would bring close by. So that's how the compasses work, that the Earth is producing a magnetic field, and then that exerts a force on the magnet that's inside your compass. Okay, so those are the most basic way of producing electric and magnetic fields. But it turns out that there are other ways of producing these. And so let's talk first about the electric field. So the electric field can be produced by having charges, but something that was realized in the 1800s by a physicist named Faraday is that if you have a moving magnet, and so therefore a changing magnetic field, that will also produce an electric field. And we've actually seen an example of this physics. So remember when I was talking about microphones, I said that when you have a magnet that's moving relative to a coil of wire, that you actually induce or cause a current to flow in that wire. Well, this can be understood by this new effect that I'm talking about here. Okay, so the idea is the magnet produces a magnetic field, like we said. If you start shaking the magnet around, that magnetic field is changing with time. And a changing magnetic field will produce an electric field. So that's what's shown in blue here. And so because the electric field now is overlapping with this coil of wire, that's going to exert forces on the charges, on the electrons inside the wire, and that's what causes them to move. Okay, so this is the basic physics of this phenomena that we called electromagnetic induction, right? So the important takeaway from this slide is that changing magnetic fields can also produce electric fields. The electric field can be produced by a charge or by a changing magnetic field. And then the final bit of physics, maybe you can guess it. The final bit of physics was something that James Maxwell understood in detail and predicted in detail. And that is that there's another way also to produce a magnetic field. In addition to having a magnet or a current, there's a third way to produce a magnetic field, and that's by having a changing electric field. So if I have, say, some charge producing an electric field, but then I start shaking that charge around, then the electric field will be changing with time, and that change with time of the electric field causes there to be a magnetic field. So then what Maxwell realized is that if, say, an oscillating charge will produce an oscillating electric field, and then that produces some magnetic field, well, that will also be changing with time. And so by the induction effect, that will produce a further electric field, but will also be changing in time. And so you kind of get this chain reaction where the electric fields can cause magnetic fields, and they can cause further electric fields, and so forth. And so what Maxwell realized is if I do something like shake a charge around, then that's going to cause a disturbance where you have a magnetic field producing an electric field, then a magnetic field. And this sort of propagates outward from the original shaking of the charge. And eventually you can have electric and magnetic fields oscillating all on their own, far away from the charge that originally produced them. Okay, so mathematically, he found that the description of this propagating disturbance in the electric field and the magnetic field, that looks very, very much like a propagating wave. So here's a picture of what the electric and magnetic fields might look like at some distance from a charge that's being oscillated up and down sinusoidally. If you were to take a snapshot, of course, these are invisible fields, but if you could actually visualize the electric and magnetic fields at some instant in time far away from the charge, which is maybe way to the left of this slide, this is what you would see. You would see in some places the electric field points one direction, in some places it points the opposite direction. Similarly, the magnetic field points in one direction some places, and in the other direction other places. And then as a function of time, so if you now pressed play and watched what happens to all these fields, that whole pattern propagates to the right. Now, the very, very interesting thing that Maxwell discovered by manipulating the precise quantitative equations that describe all those electromagnetic effects, he calculated that the speed of this disturbance as it propagates away from the original cause of it, the shaking charge or moving magnet or whatever, the speed of that is independent of how you produce this disturbance. It's independent of the details. It always propagates away at this speed of 3 × 10⁸ meters per second. And so that was extremely interesting to Maxwell, because there was another phenomenon that had been studied recently where this same velocity had come up. And that was the phenomenon of light. Up until then, people had no idea light had anything to do with electromagnetism. But then they had measured the speed of light. They'd realized it propagates at a finite speed, and it's this very large speed. And that speed had been measured also to be 3 × 10⁸ meters per second. So when this came out of Maxwell's calculations, he had a eureka moment, one of the greatest moments in the history of physics, when he realized that, hey, maybe this light is actually one of these propagating disturbances in the electric and magnetic field. Okay, so Maxwell realizes at that point that light is in fact one of these electromagnetic waves that he's just understood theoretically. And so just to summarize that in a picture, here's a picture of a flashlight and an indication of the beams of light coming out of that and moving to the right. So what I'm saying is that you could actually give a deeper understanding or a deeper explanation of what that light actually is. And it's this, that the light is actually this electric and this particular pattern of electric and magnetic fields that are moving to the right and have a specific arrangement that I've shown in this picture. So this is the snapshot, and this whole pattern moves to the right at this velocity of 3 × 10⁸ meters per second. Okay, and so you notice that this pattern of electric and magnetic fields, if we focus on one or the other, it looks very much like the pattern of displacement for a wave on a string. And the mathematics of this is very much the same as the mathematics of the wave on a string or of sound waves. And so light is also a wave phenomenon, and what's waving are the electric and magnetic fields.